Good evening, everyone. Can you all hear me?
Yeah, good evening.
Okay. Yeah, in the chat, they've asked for the session to be recorded. Yes, yes. The recording, you can find it in your calendar. So you have to go to the calendar and look for that day's event. You
Hmm.
click on it, you can see a link to the session
Okay. Actually, that
last
link
week.
is not working. Actually, I get that link, but it's not working. I mean, I can't open that. I mean, it's
Okay, is it?
not playing. The video is not playing.
Okay, okay. I'll just check
Yeah,
with the instructors and then get back to you later. Okay,
sure. Please.
Okay. So this session is regarding week 4 practice programming assignments. So how many of you have watched week 4 lectures? Uh, you can raise your hands. You can, since there are not many people here, you all can unmute and talk. So we can have a,
Well, I have not watched every lecture. I have just watched few lectures of week 4,
okay.
and I still have to watch uh, direct topological sorting and depth first search.
Okay. So how are you finding the lectures to be?
Lectures are quite good. Uh, a bit
How you
theoretical.
understand?
Madhvan sir goes a bit theoretical on all these subjects, and
Okay,
that's why
okay.
I think. Yeah, well, can I ask a question? I had a doubt regarding prep, regarding extra programming so- questions. Since I was preparing for interviews, technical interviews, I found that these questions are not much. So, are there more problems that we'll get, or should we go and solve these questions from other websites?
You will get the live coding problems as well. I hope you have seen them on
Yeah, I've
the Friday session.
seen them. Yes, yes.
Also, they will be in the portal itself. Can find in the live coding part of the portal. So there you can find more problems. Other than that, you will have to look up at the competitive sites like CodeChef or HackerRank sort of sites. You'll find a lot of problems competitive. You can start from the beginning and rise your way up.
Okay. If I'm able to solve these problems that are given in our portal of graded programming assignment, practice programming, and live coding, where can you assess on a general sense that my interview, my coding skills stand? Uh, are they really beginner level, or I can say I have gained an intermediate skills on programming, the regarding algorithms and data structures?
Uh, I would say concept wise, you would have understood all of it. I mean, the concept will be covered, but there are a lot of different types of questions you can face in interviews, right? There are a range
Yeah.
of, so that you will only get the experience once you solve more questions. I mean, you will be able to assess what you will have to use. For example, if you get a question on DFS or which you need to use DFS, you will know what to do, but the type of question will be such that if you don't practice, you will not be able to apply it
Okay.
uh, in the interview will all, on top of it will be a pressure situation, so it will be better, it will be like much better if you practice it in the competitive sides as well on top of solving these.
Okay. Okay. Thank you, Harish.
Yeah, sure. Okay, so I see that most of you have not watched the week 4 content, so maybe so how many of you know about the graph data structures? Like, are you all familiar with graph data structures, graphs? Okay, Vasudev is aware of it. Good. Okay, so week 4 is an intro to these graph structures, data structures. So basically, and then searching through these data structures, and this is the general what the week 4 syllabuses. So let me just share my screen. Can you all see the screen? Is it visible?
Yes, sir, it is visible.
Yes, it is visible.
Okay, okay. So before before we get into these problems, let's just have a quick overview of what week 4 is actually and what graphs in particular are. Just a graph. So I'll just try to, for example, uh, so we have graphs are just data structures that have like vertices. These are the vertices, or you can call them nodes, ABC, and edges that connect them. Edges. A to B is connected by an edge. So this is a graph. So these are the lecture slides. So, for example, the Sheila is connected to math. So that is a connection. So there are two types of graphs actually, directed and undirected. Okay, just give me a minute. Okay, so this is the data structure that we have, graph. So how do you think we can represent the graph in our code? Like how can we represent them? Does anyone have any idea? For example, we are given a set of vertices like 0, 1, 2, 3, 4, 5, and uh, edges. For example, these are
Using matrices.
matrices. Yes. How can we do that using matrices?
So if like we will have a two m cross n matrix where each vertex will be denoted by the index, and if a vertex is connected to another vertex, then we will have a one there, which will donate a connection, and if it is not connected, it will have zero. So it will donate it is not connected. So it will be a simpler form of connection between two vertices.
Correct, correct. That is correct. So this is covered in these lectures. So you can use two ways to represent the graph. One like he said in the Manan, right? Manan said using a matrix that is, for example, if we have a set of edges given, we can and we know the vertices like 0, 1, 2, 3, 4, 5. These are the vertices and the edges. So using this, we can use an adjacency matrix and represent the graph. For example, the 0 and 1, there is a connection between, there's a direction between, there's a connection between 0 vertex and first vertex. So you say for the 0 and 1, there is a 1. And similarly, 0 to 4, there is a edge. So 0 to 4, we represent 1. So that represents the connection. Are you able to understand this concept?
Where we have to look at 0 to 1, I mean rows and columns, right?
Yes. So the rows of the rows are so both rows and columns. This is an n cross n matrix. So we represent like both. So if there is an edge from 0 to 1, so the row 0 and the column 1, 0, 1 represents at the edge.
Okay.
A of ij is equal to 1 if ij is an element, ij is an edge. Right? Is that clear?
Yeah. Yeah. Yeah.
Okay, so this is one way of representing an adjacency matrix. A graph, sorry. So this is, so the first case was for a directed graph. So the directed graph has directions. For example, you can go from vertex 0 to vertex 1. So that is a directed graph. And undirected graph has no direction. So you can go from vertex 0 to vertex 1 and you can come back as well. All the edges are in both directions. So that is an undirected graph. So in the undirected graph, if you just see the diagonal, both sides of the diagonal will be same. So there is a connection from 0 to 1 and from 1 to 0. Right. So both ends will be symmetrical. So if you cut through, like if you cut this diagonal like this, both sides will be symmetrical. Right? Can you see it? There's the one here, same, because it is a undirected graph.
The diagonal which you are talking about is between 0, 1, 1, 0. This.
Yeah, the diagonal, this one. Can you see the cursor?
Yeah.
So the diagonal of this matrix. So if you just take
All
all the
zeros.
zeros, the diagonals has, yeah, all zeros. So both side of it will be symmetric because
Okay.
if we have a connection from 0 to 1, if there is an edge from 0 to 1, because it is an undirected graph, there will be edge from 1 to 0 as well. So both will be 1. Similarly, 0 to 2, if there's a vertex 0 is connected to vertex 2 through an edge, you can, from 2 to 0 also there's a connection. 0 to 2, 2 to 0.
Okay.
Right. So if you see the diagonal, it is symmetric.
Yeah.
Yeah, so that are the directed and undirected graphs, 2 types. So computing neighbors, okay. So adjacency matrix. So this is how do we get this representation? Maybe I can show it in a collab. Just give me a minute. Okay, so these are basically the same example as in lecture. In the lecture, you can see this example, right? Set of edges. So these are the edges. So if you say, for example, these are the edges. It is just initializing. So this is the directed graph. And if we take the undirected graph, then both, so there is a connection from 0 to 1. There's an edge from 0 to 1 and from 1 to 0. 0 to 2, 2 to 0. So this is just for illustration.
So this
Okay, so
diagram you have, this is in the Colab, right? You are
this is in the sheet. Yeah, I've just screenshotted it.
just screenshot.
Same. This is not output.
Code.
No, this is not the
Okay.
output. So this is the graph that we are using these edges.
Okay.
This is the edges I just wrote. Okay. So this is the matrix. So this is using NumPy. You can use NumPy for matrix calculation. It is easier. So this is a 10 cross 10 matrix, right? So these have 0 to 9 vertices. So this is 10 cross 10 matrix. So first you initialize it, and then for each edge, for each ij, that is the edge for each ij, that is for each edges, like for each edge, you initialize the matrix A of ij as 1. So we get this representation. Right. I hope this is clear.
Mm.
Yes, sir.
Okay. So now to calculate the neighbors, for example, what do you mean by neighbors? Okay. So if you give the neighbors of 7, how do you calculate the neighbor? Like, what are the neighbors of 7 in this graph?
Two edges to which
Yeah, which are them? Just
it is
which,
connected.
4, 5, and
yeah,
8.
vertex.
8.
Yeah,
4, 5, 8.
4, 5, 8. Yes, the edges that are connected to 7. So how do you calculate the neighbors? So this is the 7. So
Hmm.
these are the edges, right? Wherever the 7 has 1, 4,
That are neighbor.
5. Yeah, they are the neighbors. So that is just a function to find them out. 4, 5, 7. We just use a list. A mat dot shape will give the rows and columns of basically. So it will give 10 cross 10
AMAT is the matrix name.
matrix name. Yes,
Okay.
matrix name and I. Yeah.
I
So
is
it
the
means
edge.
one row will represent the neighbors of that particular number.
Right. For example, the first row here it is 0, so it will give the neighbors of 0, which are 1, 2, and 4.
Oh,
Right. So here 1, 2, and 4 are the neighbors. So we'll just check for if this is 1, if a mat of ij. So here I we are giving as 7 neighbors of a comma 7. So it will check which all are 1. For 7, it will be 4, 5, and 8. Right. So that will be an output. That will be the output. The list will be the output of this function. So I can also represent. So this, since this is this graph that we are discussing, I'll run this edges. So I'll run the matrix again. So this is the symmetric matrix we are talking about, and the neighbors. So this is giving 4 and 8. Okay. Oh, I didn't run this part. Okay, so you can see, right? 4, 5, and 8. This is the same code in the column. Okay, so adjacency matrix is clear, right?
for which edges you conducted this adjacency matrix?
7, right? Neighbors of A mat 7, vertex 7.
No. In the above, you said that there were 2 graphs. So for
Yeah.
which graph you?
So since in the lecture we use this graph, that is the undirected graph.
Hmm.
So here also I use the second edges. So these have
Second.
both.
Okay.
Yeah. These are the undirected. Both directions there is. This is just for illustration. I have usually you can just write one set and then program it to find the other way also. This is just for easy understanding. I've written like this.
Okay.
Okay, so that was about adjacency matrix. The second representation, how we can represent graph, is using adjacency list. So this is simply you are just taking the vertex and yeah, here. So we are just taking the vertex as a dictionary and we are representing all its neighbors, basically all the edges that it is pointing to, all the connections, edges that it is pointing to as a list. So the key will be the vertex, and the values are a list of all its neighbors. This is the adjacency list representation. Is this clear?
So for each edge, there is a list of its neighbors, and
Yes, yes.
they are you mentioned using the list function.
Why 2 is not the neighbor of 0?
So
Incoming
from
edge.
2 there is an edge to 0. Yeah, this is a directed graph. Is there an edge from 0 to 2?
No, sir.
Yeah, so
So we
this
are
is a directed graph.
Sorry,
If
we are
it was
just
an
considering here the outgoing edges from each node, right? As its neighbors.
yes, and yeah. So edge is just that from V2 to V0 is the edge. There is no edge from V0 to V2. Like vertex 0 to vertex 2, there is no edge. There is only an edge from vertex 2 to vertex 0.
Okay, sir.
Right? Then this is the directed graph. In the directed graph, the directions are important. Okay, I hope that part is clear.
Yeah.
So this is just the representation. You will just initialize a dictionary, and first initializing it to an empty list. All the values like of all the vertex we first initialize for 0, 1, from 0 to 9. We initialize an empty list, and then from wherever there is an edge, we just append that edge, value of that edge. That is what this part of the code is doing. I'll just show it here. So, okay, so since we were using this example, right? Let me use this. This is the example we were discussing here. There. So let's just use these set of edges and adjacency list. Right. So 0, 1, 4. This is the representation. Is the adjacency list clear to everyone?
Yeah.
Okay.
So is it a list or a dictionary?
It is a dictionary, but it is just called adjacency list. It is just a notation. Like that is how it is called. But it is a dictionary, but all the neighbors are stored as a list.
Okay, sir.
So in the previous case, it was a matrix. So here it is just the terminology. Don't get confused by it.
List inside dictionary.
Yes, correct.
Matrix
List.
is also a list of lists. Matrix is also a list of lists in Python.
Matrix is a matrix. Yeah, it is a set of. You can also set of list of list, right? That is what you are saying.
What we represent in the Python is a list of lists.
Yeah. In a way, yeah, that is right. But just for the terminology and for the understanding sake, we are just calling it a matrix. So it is easier to understand, right? If you represent it like this. But when we code, you can also represent it as a list of list, or you can use NumPy also and use it when you code. Okay, so these were the basics. Yeah. So what do you think? Is there an advantage of using either one of them? If you use a adjacency matrix or an adjacency list, what do you think is an advantage you are getting?
So adjacency list will be much more advantageous.
Why?
So because it's taking less space and less number of comparisons will be performed in searching.
Yes, that is correct. It takes less space. Yes, right. So it all depends upon what we are using them. So if you want to find the neighbors of say vertex 0, then obviously the adjacency list is a better because you can directly get the neighbors from it, right? So if you want to find the neighbors of 0 using the adjacency matrix, you'll have to iterate through the entire row 0, right? To find the all the neighbors of any vertex. So that is an advantage you have over adjacency list has over adjacency matrix.
Complexity
Right.
will be less.
Yeah. But it is easier to check. For example, if you want to check whether there is an edge at 4,3, then which is the better representation? If we just want to check whether there is an edge, whether there is an edge.
Matrix.
Yeah, correct. So you can directly check it like 4,3. If there is a 1, then there is an edge. But since this is a small example, but if the list is a big one, so you'll have to iterate through the entire list to see, right, whether there is 3 in it. So this can be done quickly using the matrix. So these are just few advantages and disadvantages. So depending upon your usage, you can use either of the representation. Right. So those were just the basics of week 4.
What is reachability?
Reachability.
Yes.
So where do you come across that? Like you mean reaching?
In this slides only.
So I think so reachability. Okay. So these are 2 ways using so breadth first search and depth first search. Okay, this will come like in the next part of the lectures, in the next coming lectures. So these are the ways how you can iterate, like search through the graph. Okay, we'll come to it.
Okay.
Okay, so there are like so this is the first. There is breadth first search and okay, so how do we explore the graph? Suppose if there is an edge from if there is a so this graph structure is used basically. So how do we like find out whether we 0 if we can go from 0 to 9? So this is the reachability from 0 to 9, right? Like from 0, which all other vertex can we reach? So we need to find out, right?
Yeah.
So there are 2 techniques. One is breadth first search and one is depth first search, which we can use to find this out. So breadth first search is basically we start at 0 and then we see all its neighbors. Okay, I'll just directly take you to the example. Okay, so this is the basic technique of how we use so I'm just going through all the like on a top level. Okay, you'll have to watch the lectures later since most of you haven't covered it yet. So I'm just trying to brush through all the concepts so that we can go to the BPS. Otherwise, if I start BPA, you will not be able to understand what I'm trying to say. If I say BFS, suddenly you will not understand what it is. So that is why I'm just trying to brush up everything, or rather just give an overview. So okay, so BFS is basically for example, we want to see the reachability of vertex 7, like from vertex 7, where all we can reach, which all part of the graph we can reach. So that is basically what the reachability was asking. Like someone asked me what reachability is. So suppose from vertex 7, where all we can reach, like which all part of the graph can we reach?
Okay.
So to explore that, so in using BFS, for example, we start at 7 in this example, and we use a queue. Okay, so this so visited is basically to check whether any vertex is visited or not. So starting from vertex 7, so first we mark 7 as visited, and then we put 7 inside the queue. Right. So now 7 is visited. So now we check all the neighbors of 7. What are the neighbors of 7?
4, 5, 8.
4, 5, 8.
4, 5, 8.
Correct. So that is after marking 7, we explore the 7th vertex. So that is, we visit all its neighbors and put them in the queue. All the 4, 5, 7 are marked as visited, and then we put them in the queue. Okay.
Yeah.
So then so let's say we put them in the lowest first, and then so 4, 5, 8 is the, so in queue whatever
Order
we
is
insert.
also important, right?
Yeah, so that is how we implement. So in this case, we have implemented when we see 7, we go for the smallest neighbor. So here it is 4. Then first we insert 4 into the queue, then 5, then 8. Okay. So since this is a queue structure, so we first what happens in a queue? What is the logic we use?
Delete from the front and addition at the rear.
Correct.
First
Correct.
in, first out.
First in, first out. Right. FIFO. So 4 was the first in. Right. First. Yeah. So we then explore 4. What are the neighbors of 4?
0 and 3.
0, 3, and 7 is already visited.
Visited.
Right. Yeah. So
Sir,
yeah.
suppose we would have been written 854, then we have taken 8 first. Is it so?
Yes. So suppose that is how you implement, right? These are all codes. If you say that we have implemented that way, so here we are saying we have implemented that if we go to any vertex, we first insert the smallest neighbor, then that way. So ascending order. So that is why 4, 5, 8 went. So if you have, say, 8, 5, 7, 4, you have inserted in the queue. So then whatever is the first one, you take it out.
Okay. Thank you.
Right. So 4 is done. So next is 0, 3 were the neighbors of 0 and 3 were the neighbors of 4. 7 is already visited. So we insert 0, 3 as well. So and then we explore 5. Right. Next in the queue is 5. So similarly, we go on. What are the neighbors of 5?
3, 6.
3, 6, 7, 8. Right.
Yeah.
So 7 and 8 are already in the visited. They are already true. They were already visited. So we just insert 3, 6. And similarly, we go on with the next one. Next was 8. And we see that 9 is the only one left, neighbor of 8. And we insert 9. And then we explore the remaining. Okay, so 0 has 2 more neighbors which are left, right? So when we explore 0, those will get covered as well, because only 0 can reach them. Yeah. So that way, so at the end, we see that from vertex 7, we can visit all other, because all other vertices this way, since we have explored it this way. At the end, all of them will get explored. This doesn't make any difference because we have already covered everything. But at the end, the queue will.
So
Yeah.
where in this we are saying that we are starting from 7 and then we are visiting its neighbors and we are putting it into the queue, and then we are checking for those neighbors if we can reach to its subsequent neighbors, and so like this, right? In the
Correct,
ascending
correct.
order.
Ascending order, you don't have to like don't think about that as a ascending order or descending order. It is not always. It is how we implement. Here, just for the sake of it, we are saying we can implement in descending order however we want.
Okay.
That is not how. But the point is, we are using a queue. Whatever we insert first will come out.
Okay.
So, so that is so we are going layer by layer, right? So that is why it's called breadth first search. So if we start at 7, we first cover all its neighbors. We put them in the queue, and then go for the next minimum, cover all its neighbor, and similarly we go on. So that is one implementation of like this reachability, how you check. This is how breadth first search is implemented. Is there any more doubt on this topic?
This was the whole
Okay,
concept
so
of BFS. Means we are taken 7, we can take any other vertex, right? And explore
What
for that.
conclusion we get from doing all this process?
Okay, I'll take one by one. What is the first question?
My question was in BFS, we can go from any vertex. Here is the example of 7. We can go with any other vertex, right? And start from
Yeah,
there.
yeah. Right.
Okay,
Okay,
sure.
when I just explain the code as well, so in that it will be clear. Okay. So the next question, what was it?
Actually, what conclusion did we get from doing all this process of adding queue, deleting from queue, and then
Your voice is very low. Can you just increase your voice volume?
so my question is, what conclusion do we get from doing all this process of BFS?
Okay, so there are certain advantages of BFS. So this is what we are using is, so we are from 7, we were trying to figure out where all we can reach in this graph data structure. From any vertex, which other vertex can we reach? So the reachability is what we were trying to find out. So one way to do that is using the breadth first search, BFS. So this is one way of doing it to find the reachability, right?
So then, how we get the reachability of 7 here? What is the reachability of 7 here now after doing?
So the visited, so this visited, usually it is implemented as a dictionary. So all its content, like all of it becomes true, right? That implies from 7, we can reach every other vertex. So that is how we started. From 7, there is an edge from 7 to 4. So we first see the neighbors of 7.
Okay, sir.
Then, so first neighbor was 4. So then we, 4, 5, and 8, we put in a queue. And then we start checking the neighbors of 4. So till we all, like till wherever we can reach. So that ends, like when all the iteration gets over, when the queue becomes empty, we'll find out from 7 where all we can reach. Right.
We can conclude that from 7 vertex, we can reach every vertex.
In this particular case, yes.
In this particular case.
Right.
Okay, sir.
So that will determine. So once
if it was a directed graph, then it would have been different, right?
correct, it would have been
Or
different.
undirected graph, so we can reach anyway, any node.
Right. So for example, so yeah, so since this is an undirected graph, you can it was easier. So we were able to reach every other. So it depends upon how what are the edges and how it is.
Yeah.
Right. So let's just quickly run through the code of BFS. So BFS implemented using the matrix, adjacency matrix, right? So this is how it is. So first we find we were talking about the visited dictionary, right? Before we were checking. So first we initialize that visited, and then we initialize all all the rows, that is from 0 to 9 as 4. Like we give it as a key of visited, and we initialize it as false. Right, at the starting of it, everything was false. Right. So this is the initial.
Explode.
Sorry.
Visited means the node. Visited means the node which have been explored. Same synonymous to that.
Yeah. So visited, we are so visited is the dictionary we are trying. We'll keep like we first initialize all the nodes. So for example, we started from 7, right? As we reach all the other nodes from 7, we change them to true. So that implies from 7 we can reach all other nodes. From which all nodes if this turns true.
My
Yeah.
question was visited and explored. We gone through the BFS, explore, then get the list of the connected nodes. The explored means visited. Whatever
Yes,
we
yes.
are using the code, the same synonymous thing is that what is explored is the same visited.
Correct.
Is it so, no, sir?
Yes. Once we explore, it is visited. So we turn it so here, right?
And how
When we
visited is defined in this code? How we recognize that this is visited one?
yes, I'll come to that part. It is here.
Yeah.
Okay.
Yeah.
Yeah. So Q we use. So Q we will also implement Q. Okay. So you all know how to implement Q, right?
Yeah, sir. First in, first out.
Yeah. So that we can implement using a class. I think it was done somewhere here. Yeah. I'll just quickly run through this also. So this is how the implementation of Q is. So it is as internally as a list we use it, but we use a function add to append to the list. We keep on appending it using this add function. There's a delete function that removes the first element of the queue of this list, right? It is the internal implementation. So we remove the and returns the value, return v. That is what the delete function does, right? And there is an isEmpty function that checks whether the queue is empty or not. So this is the implementation of the queue. Okay. Is this part clear? Like, is there any doubt here? Because we'll be using this in the BFS code. Okay. So that queue we'll use in the BFS.
This capital Q is same. You can write capital Q function. Capital QUE.
Yeah. So that is how. So that is how we have initially. So class Q, right? So this is what we are using. Q. We have used capital Q here.
Okay.
So that is why we have to. Okay. So then V is the given element, right? Before it was 7, so we give V is the vertex we want to check. From V, we have to check all the other parts of the graph. So we first initialize visited of V as true. That was the first step, right? Mark 7 as true and add it to the queue. This is the first step we are doing here. And then we add it to the queue.
The class Q, we are using a small q. A small q is an object of the class Q.
Right. Yes.
Okay. Got it.
We'll be using this queue.
Yeah. And a small q is the object of the Q.
Class Q. Yeah.
Okay.
Right. So q dot add means we are using the add function we have just about we just saw, right? About, and we are adding V. V means the first vertex to it, to the queue. Right. So this is the first step. Mark 7 and add it to the queue. So then this part of the then we go like the while loop is the next steps. So if the queue is not empty, that is the terminating condition. We remove the first element. J is equal to q dot delete q. So in the delete q, we were removing the first element, right? Here. Yeah, if you all remember, delete q returns the first vertex, right? So and it also removes from the queue. So right. So J is the first vertex. So in this case, it was 7 because since it's the first time we are running the loop, it will be V, whatever V it was. Then for k in the neighbors of neighbors, we just discussed the function right here. So this is what they are using, this function, neighbors function, which returns the neighbors of
So we
any
are using
vertex.
adjacency list or matrix?
Matrix. You're using
Okay.
matrix, right? A mat.
Okay, sir.
So since we are using matrix, we need this neighbors function, right? In matrix, if it was a list, we could have directly found out the neighbors. So since it is a matrix, so for k neighbors of mat comma j will return a list, right? With all the neighbors of j. Okay.
It means only that particular row will be
Yeah.
of J.
Yeah. So this was so once we have 7, we check what are the neighbors of 7. So neighbors of 7 are 4, 5, and 8. So this is what it will be like in the first case. That is what it will be returned. Sorry, not this one. This one.
V must be given, na, sir. V must be given, na? As a
V will be
parameter.
given. Yeah. I said BFS.
Same V we are using in the visited V, na? Same V is
Yeah.
there. Okay. This will be
So
given.
V is the starting vertex. So from V we are checking all the other. From V where all we can reach, right? Reachability we are checking.
Yeah.
So neighbors will return all the neighbors and we'll iterate through them using this for loop. If it is not visited, then we add it to the visited dictionary and we add it to the queue as well. So that this is just the code for what we just talked about, right? So first we add 7 to the queue, then we check we remove the first explore 7. We see what are the neighbors of 7, 4, 5, 8, and then we add it to the queue. Also, before exploring, we delete it, right? So here is the first we delete, then we see the neighbors, and then we mark that we have seen all. We can visited. We mark as true, and we keep. And then this will run till the queue is empty. I hope this part is clear, right? This is basic, very straightforward. Any more? Is there any doubt in this? Because we'll be using this in the PPS. Okay. So this was the first implementation, breadth first search.
Sir,
Yeah.
sir, what is the advantage of using queue? I mean, sir, we could simply append in the list. We could make a list and append it and take an element from it.
Yeah, we can do that. So instead of queue, you can just use the list directly, and then we can remove the first element, right? That's what you're saying. First take the first. You can do that way also. This is just for the understanding. So it is better, easier to understand, right? If you create a different class, you can do that way as well. It is how your preference. Doesn't make any difference.
Okay, sir.
The concept of first in, first out should be implemented somehow, either that way or this way.
Okay, sir. Thank you.
Yeah, so that was the first, breadth first search, and then there is one more. The second one is depth first search. So like the name suggests, it is I'll directly go to the example. Okay, so in the depth first search, so here DFS we are starting from 4. Let's say in this example we are starting from 4. So before what in the BFS, what would have been the next step? We first put in the queue and then remove from the queue, and then what do we do? If it was BFS.
What have you told, sir? Again, first.
So if we start from vertex 4, we start a BFS. What will be the first set?
See the neighbors of 4, sir, first.
Neighbors of 4, right?
Yes, sir.
0, 3, and 7. That
Yeah.
we'll do in BF. So in DFS, instead of going to all the neighbors, we start at 4 and then we see the first neighbor. Once we see the first neighbor, we stop exploring 4. So let me just show. Okay, so we start at 4, we mark 4, and then we suspend 4, and we see the first neighbor, and then we do not see the rest. We suspend it there, and then we start exploring that neighbor. So
We
it is
have
going,
to only select one neighbor of all the
yeah,
neighbors. So that
yeah. In this implementation, we are using the minimum, right? Which are so 0, 3, and 7. We just see the minimum. That is how. Say in this implementation, that is that depends on your implementation. So here we see the lowest neighbor of 4 of any vertex. So we start at 4, we see the neighbors, and we see the lowest neighbor, and then we suspend like looking for the other neighbors of 4 and start exploring 0. That is the neighbor of 4, first neighbor of 4, right? So, and then we see the neighbors of 0. That is the first lowest. There are 2 neighbors, 1 and 2. The lowest is 1. So we explore 1. We suspend 0. So we go in depth. Like instead of going from all, like putting it in. So in the here we are using a stack to do this, because so what is the implementation of stack? How does stack work?
Last in, first out. Leave first, last in, first out.
Last in, first out, right? First in, last out, last in, first out. Yes, correct. So that is why we are using the stack, because first we mark 4 and we put in the stack, and then we suspend. We do not take it out. We explore its neighbor, and then we put that in the stack, and then we explore its first neighbor, right? So we keep on adding to the stack. From 1 we go to 2. So once we reach 2, then the 2 doesn't have any more neighbors, that is not visited. So we go back to 4. So now we take from so once there is nothing else to explore. So once we reach 2, there is nothing else to explore. So we take, so from the stack we take the last element that has been like put in the stack. So if you see here, first we put 4 in, then 0, then 1. Then we came to 2, but there is nothing. 2 doesn't have any more neighbors. So we remove the last element from the stack. That is, we explore 1, backtrack to 1. Right? Because it is a stack, whatever we have inserted last, we have to remove first. So after 1, then 1 doesn't have any more neighbors. 0 also doesn't have any more visited neighbors. I mean non-visited neighbors. So we remove, backtrack to 1, backtrack to 0, and then we backtrack to 4. Here we mark. So after removing as well, we mark it, like we put it back again, and explore 3. So, because it has more neighbors. So we only like remove it from the stack and if it doesn't have any more neighbors, right? In the case of 0 and in the case of 2, 0, when we were backtracking, there was no more neighbors. So that is how this we do this operation. So like we started from 4, we went to, so this is how depth first, because we are going deep instead of going like in the breadth first search, we are going depth wise here. That is the difference. So we first started 4, go to 0, 1, 2. Then there was no more, so we backtrack to 0, 1, and then come back to 4. Then check the next available neighbor. So 3 was not visited. So we explore 3 and suspend 4 back. We put it back, we suspend 4 and put it back in the stack. And then we do the same. We check its neighbors, and then we keep on doing till there are till the stack is empty. So this is the depth first search implementation. Is this clear?
Yes, sir. Yes, sir.
Yeah. So the stack becomes empty and all. So because from 7, from 4 also we can reach all other nodes, right? Okay. So now let's see the code.
In DFS suspend is equivalent to visited or explore is equivalent to visited? Explore.
Explore. When we explore, mark it visited.
Okay.
Yeah. First, for the first time when we see something, when we explore it, like we mark it as visited. Okay, so this is the implementation of the same. So since we are using a stack here, instead of stack, the recursion in Python, like recursion itself is a stack, right? So we can use recursion as a stack operation here. So let's say, okay, so this is the function. Visited parent. Okay. So this is using implementing DFS using the matrix representation. We give DFS visited parent and V, the vertex. So we are just checking. Okay, so here the first function we are using to initialize. Okay, this part is we take the matrix and we initialize its rows and columns. A mat.shape will give the rows and columns. Visited and parent are dictionaries. So here we are also tracking the parent. For example, the parent of 3 is 4. Right, that is the parent representation. Okay, before we do that,
How can we say parent is 4 only? Because it is connected to others also. No? 5, 6 others are also connected.
no, this is via parent. We are using it to backtrack. So, for example, yeah, we use the parent to backtrack, right? When from 4, so suppose sorry.
In DFS, it is parent. 4 is parent.
Yeah. Even in BFS, 4 will be parent of 3, right? We start at 4, we explore 0, 3, 7. So yeah, so this is so we first initialize. So parent we are using just to backtrack everything. Say so first visit. So first all the parent are initialized to -1. So similarly, I think this slide doesn't have it. Okay.
Fluctuating.
Yeah. So there was one representation of parent as well. I think it is there in the BFS slide. Okay. Well, is there a problem? You are able to see this slide, right?
Now it is okay.
Okay.
Not flickering.
Okay. Okay. So parent. Okay. So we are initializing first visited as false and parent as -1. Like this is just initialization because parent cannot be -1, right? So -1 represent. It has not been. There is no parent yet. So and we return these two. Okay, so this is just the initialization. This function is for initialization. The second function is what we use to calculate the DFS. So first visited, first node. V is the first node. That is in the double case, it was 4. So we mark visited as true. And then we see the neighbors of 4, right? So this loop runs through the neighbors of V, and if it is not visited, then the parent of so K. So in the case of 4, the first neighbor will be 0. So if so 0 will be K. So if 0 is not visited, then we mark the parent of 0 as V, that is 4. And then we call visited. Okay, so then we call this again. So this is the stack implementation. So using recursion, we are implementing the stack. So so like when we call this part of this, so this DFS will get suspended and this will get started. That is the internal. So that is in turn acting as a stack, right? Is this clear? since we don't need a different class, we can use the recursion as a stack.
Once again, sir, this is confusing.
Yeah, so this stack we were using it, right? Stack to suspend us. This stack is what is being implemented here. So we are calling the same function. We are calling this same function, but we are checking from k. So in the first case, when we start at 4, first we see the neighbors, that is 0, 3 and 7. So we start, so 0 is the first neighbor. So first k will be 0. So if it is not visited, we go in, the parent of 0 will be 4, we initialize here, and then so we call the same function using 0 now, right? So this 4 will be suspended, we go to 0, like how we were doing before. So now this function will be from 0. So because 4 was already visited, when it is in 0, the next neighbor will be 1. Right. So this function keeps on calling itself, like with the next. So the stack representation, I'll just move up, is what is being implemented here. Initially, it was 4. Here, it was 4, right? So first, it calls from 4, and then it goes to 0, and then we call the same function from 0. So that is, this is what is happening here. Then we go to 1. So this stack implementation is being done using recursion. Is it clear?
Yes, sir.
Okay. So this is the basic concept. So it will keep on going till it is not visited, right? So once it is visited, so it will as and when. So if it sees in this case, if I scroll up again. Okay. So once we from 4 we go to 0, then we go to 1, then we go to 2. So 2 doesn't have any more neighbors. So that function will get function will terminate, and it will go back to 0. It will backtrack to 1. It will backtrack to 1, and then from 1 it will backtrack to 0, and then it will backtrack to 4. So function. So this is what is acting. This is what is acting as a stack. That is how it keeps same thing is implemented using this function. Okay. I know it's a little confusing, but if you just think about it, you will be able to understand. So visited and parent is what? So every time the updated, the visited and parent is being returned. Right.
Visited, hello.
Yeah.
So visited and parent are global dictionaries, no? Means, they should be outside DFS definition.
Yeah, that so we have initialized using the other function, right? So we have
we have not declared them anywhere.
no, we are passing the visited and parent as a parameter here, right? Okay, so this will calling part will be done outside. I can show you an example here. So this was the web search. Okay. So DFS, right? Okay, so suppose we have these many edges, and we initialize the adjacency matrix, right? Yeah, I'll just print as well. So this is the adjacency matrix we are using.
Please enlarge, sir. Slightly enlarge.
Okay.
Yeah.
Will fine now?
Okay.
Yeah. So this is just an example. Okay, these are the edges I have. So these are the adjacency matrix. And we see the neighbors. So this function is just for neighbors. We need the neighbor function right here. So for this part.
Yes.
Okay, so this is the function. So once we initialize this function and then we call it. So first we have to initialize, then we have to call it, right? So this part we have to do separately. I hope this is clear. This we'll first call this function, then we call this function.
Yes.
So visited and parent will get initialized first because of this function, and it will give it true.
I was confused because the visited and parents are declared in another function, in DFS function.
Oh, right.
So I got
Okay.
this.
So yeah. So you have to first use like visited and parent. You have to initialize first, like how we have done here. Initialize these two, and then you have to call this function using the initialized visited and parent.
Yes,
Yeah.
yes, got it.
So that will give, this is the visited dictionary, and this part is the parent. Using this
But-
parent, we can, yeah,
Thank you.
okay.
These are standard functions, no? There's a DFS and BFS. We will use
Yeah.
it frequently, no? In future.
Yes. This is what we'll be using it to solve the GRPS, PPS, everything.
Okay.
Like these are like a little, you can obviously improve the efficiency of it, but this is just for the understanding purpose.
I wanted to ask you this, not for this week 4, whether this DFS and BFS will be used in the week 12 also for the solving problems, or it is limited to this 4, 5, 6.
We'll use the concept of in week 5, I guess. 5. So not in 12. Maybe no. Won't be used in every week, but in some weeks it will be used later on.
Okay.
All right. So now I think we can get back to this question, PPA 1. I hope BFS and DFS is clear to everyone. Is there any more doubt regarding this? Because these are the fundamentals. You need to know them. Graphs, DFS, BFS, are very basics. Okay. So let's go to the first question. Yeah. Yes. All right, so this is the PPA 1 of week 4. So we are given an undirected graph G. We have to write a Python function to compute the number of connected components. A set of nodes from a connected component in an undirected graph. If there exists a path between every pair of nodes in this set. I mean, a set of nodes form a connected component in an undirected graph if there exists a path between every pair of nodes in this set. Okay, so we have to write this function. It accepts a list of vertices and edges, and a list of tuples that represent edges, and returns the number of connected components in the graph formed by vertices and edges. Okay, this is the input they're talking about. Vertices and edges are the input we are given. Okay, so all right, so this is the example. Okay, so we have to find the components. Is basically so in layman terms, in this graph, this is a component because this graph 1, 3, 4, 7 are connected, but the 5, 6, 8 is not connected to this graph. So these have 3 different components. So this part is one component, 5, 6, 8 is one component, 2 is one component. So we need to find the count of this. How many components are there in any given graph, in the given graph? Right. Is the question clear?
Yeah, it is visibly 3, but we have to find the code for that, right?
Correct. We have to find the code. We are given vertices and edges. Using this, what is vertices? It is a list of vertices. So input is vertices will be the list. So in this one there are 1 to 8 vertices, and then we'll be given a list of edges, right? list of tuple. Okay, tuples, like for example, so tuples as an edge, 1, 1, 3, 3, 5. So those are the edges. These are the input we have given. You have to use this input and find the components. Okay. The question is clear, right? Okay. So once we start solving, so how do you think we can use whatever we have learned till now? How can we use that to find this out? Is there, can anyone think of something? I'll give a hint. Okay, if we use BFS, how can we find components using BFS? Okay, for example, let's say we start BFS at 1. What will happen then?
It will see the neighbor of 3, 1,
Neighbor of 1, which is
3.
3. Then what will happen?
Neighbor of 3,
What are they?
4, 7.
4, 7. And what will happen now?
Stuck.
Stop.
Stop. BFS will stop. But we already have the number of vertices, right? So we have seen these many, and we have the number of vertices. How can we use this to see? Like we have. So what can we do next?
We will number this where it is stopped. So counting will start. Counting 0 will start, and then we will add 1 counting and then start with the next vertex. Is it so?
You're partially correct. You're partially correct. So what you're saying is we'll count these, right? When we see 1, we say 1, 3. So we have 4 vertices we have visited, but in total.
In the beginning, we start the count, started count 0.
Okay.
And then we will start from the first vertex. And when it will stop, then no, counting will be in the last. Because when it will stop, then counting will be there.
Okay, so any other ideas?
I think whatever you can say vertex you are visited, we can say that visited is true. And
Okay.
after that I will go on, right? Whatever was other, let's one graph, first graph. If it is reached 3 and 4 and 7, then earlier then I will do vertices equals to 3, 4 and 7 are true. After that I will go on second, you can say second graph. I will do this kind of thing, and when I move, then I'll be increment my count.
Okay, you're correct. You're almost there. Okay. So how do we shift? Like, so first we start, for example, we start from the lowest vertex. We start from 1, and then we find this BFS is done. Then we'll start another BFS. Is that what you're saying?
Yes.
From the next lowest, which is not visited, right?
Yes, not visited.
Correct. So once the BFS is done, we'll mark this as count is equal to 1. And then we find the next lowest vertex that is not visited, and we start a second BFS.
Yes.
Once that is done, we keep on going. Yes. Will this work?
Yes, it will be on.
Correct. Very nice. So
how did you tell that? How to shift from first graph to second graph?
Because we are, see, in the input we are given the number of vertices, right? Once we say these 4 are visited, but we know which all are not visited vertices. So since this is, so we can.
Here it is visible, but in the code we will not be seeing this graph, no sir. Suppose 1 lakh nodes are there, then how to know that?
Initially, every vertex will be. I'll be put every vertex visited is false. When we reach any vertex, I'll be say visited is true.
Yeah. So when we mark it as true, it means we are visited.
I will not go again.
So we see the. So we see the visited dictionary and see which is not visited. The first instance that is not visited, we can start the BFS from there again, right?
Yeah. Not visited and visited.
Yeah, correct. So maybe we can try to implement it. Okay, so since we have already understood the BFS, I will directly bring that code here. Okay, that part we don't have to write, right? Okay. So first we'll need a queue, right? Okay, so this is the queue. So the queue, I think everyone has understood. The queue has an add function, a delete function, and is empty function. And this is just for returning. This is not important, but yeah. So these first three are the main important part of the queue. So let's just to clear the concept, let's write the BFS function again. So BFS function, we use it to see the visited, right? Which all has been visited. So we'll start. Let's say BFS. We'll use the list representation because it has all the neighbors. Okay. So what is the first thing we do?
Take one metric, two metric, one dictionary will be take that will be visited.
Okay, visited. What is the initialization for visited?
That will be every vertex, whatever vertex present. I'll be say everyone is a false. Every
So we can say vertices as well.
Yes.
So will this work?
As visitor of I equals to false.
False. Right. This is the initialization part.
Yes.
Now we call the queue like we saw. Right. And we see the first node, right?
Why sir queue is needed? Without queue you can do it.
Because in the we saw the BFS implementation, right? In that we are using first in, first out.
Yes.
So for that we have created this queue class. So
without queue also we can say a list of pop 0.
Yeah, you can do that as well. This is just for easier since this is done in the lecture, so it will be easier for you all to understand. That's why we use.
Okay.
So we first mark the first as true, right? This is the first node as true. Then what? We add it to the queue.
Add to the queue.
Okay. So this is the first step. And then the while loop. What do we check in the while? What is the condition?
I think not equals to true.
Yeah, queue should not be empty, right?
Yes, queue should not be empty, and whatever I'm checking, I'll check is it false or not.
Yeah, so this is the 15th line. We already check. If it is empty, it will return true. Otherwise, it will return false.
But already you are putting one value into the queue, so queue can't be empty, right?
Yeah, once this loop runs, we'll remove it. So if on the first value, it has to go inside the loop, right? Otherwise, we'll not be able to find. So the first operation we do is we'll remove that queue.
Delete.
Right. For K, we check all the
all the ages, whatever ages.
Neighbors. This is the neighbors. We are checking this A list of J will give the neighbors of the J, right? The first
J. Yeah. That vertex.
Yeah, first it was V in the queue, so we remove that V, and then we see all its neighbors. Right?
Yes.
Okay. So if it is not visited, instead of K, then what do? We mark it, right?
Market visiting is true. True.
Visited of
And
A
I will
is
put it
equal,
into the queue also.
and we put it to queue. So yeah, we add it to the queue. I think you have to add. Okay, yeah. Right. So this will give the all the visited, like from that from V, it will run the BFS. Right. Should return visited. This is the BFS function we just discussed before a little while ago. It's the same function.
Here you're returning visited dictionary, but question said that number of you can say connected component, right?
Yeah. We'll get to that. This is just for the BFS I have just implemented. We'll use this, right? We'll use this to see the components.
Yes, yeah. Please.
Yes. So now this is the Python function. Find components undirected graph. You just and see the spelling.
C is capital.
Okay, C is capital.
Graph
What
G
vertices
capital.
there? Okay, G is capital, vertices and edges. Okay.
Yeah.
Okay. So now what to do? Now we have vertices and we have edges. But what do we need to run this?
Connected component.
No. What does this run on?
The DFS graphs.
Those vertices which are true.
Right. But we need a list, right? Adjacency list. What do we have here? We have vertices and edges. But to run the BFS, we need a list, right? Adjacency list.
Yes, urgency list.
Yeah. We'll run the but so first we need to convert these set of vertices and edges. So we'll just see how are they. Just see what.
How did you write this one? Find components and directed graph. This function.
That already mentioned in the question.
It is given in the question. Write a Python function. No?
Okay,
Yeah.
this is required.
Now we are coming into the actual question. We'll use this BFS to implement it. So I just wrote it so everyone can. So now we'll use this later on. But yeah, first we need. We'll just first check how these vertices and edges, how are they represented. We'll just test run it. So vertices are a list of strings, right? Okay.
List of values. And that
Yeah,
is
values. What are the string? Okay. And we also have this. It can be anything. It can also be ABCD. Anyway, need not be this. Okay, so now we know how it is. Okay, now let's create an adjacency list. How do you create an adjacency list?
We will make vertices as a key of a list.
Okay.
After the
Okay, so let's do that first. For I in vertices. right? A list of I
Equal to list.
equal to list. Okay, so this is the initialization.
Yes, sir.
Now we need to find the edges, right? So I think there is some background noise. Yeah, it's better. Okay. So now, how do we like give these edges? So the edges are given like this as tuples: 1, 3, 3, 4, 3, 7. So we need to make it into this list. So how can we do that?
I'll take for I comma j, for I comma j from in edges,
In edges,
and I'll take a of I equals to on that list of append that I'll append j into that list.
append j. Okay.
Yes.
What is this doing?
So taking again whatever value has a whatever key has a edge, right? Key and edges. I think
Right. So edges is a list of tuples, like we have seen in the other. So edges is a list of tuples. 1, 3, 3, 4. So I, j is, so in this case, I is 1, j is 3. So we are just taking it. So for ij in edges, we are just appending a list of I, and we are appending j to this list. A list of i's, we are appending the j. So if there is this in 1, 3, we are taking vertex a list of 1 is equal, and we are appending 3 to that list of a list of 1. Right, I hope this is clear. So we are just creating the adjacency list in this these lines, so that we can work with the BFS.
now here if you count the key, you can say key of a list, and then it will be the my answer. Is it?
Please do this component graph the function again. I cannot.
Okay, okay. What was the first question? Key. I did not get that part. Okay, not able to hear.
Yeah.
Okay, so you want this this part?
Yeah,
Which one?
yeah, this part. Yeah, find components under undirected graph function.
Yeah. So this function, this is the function we are trying to find the components, right? So we need to run BFS from each component. So this function we have to write. We have to write the Python find component undirected graph function. We are given vertices and edges. And we are supposed to return the number of components. So we are trying to write that function. Since we are using a BFS function, which takes a list, adjacency list, using these vertices and edges that we are given as input, we are trying to construct this adjacency list. From 41 to 45, that's what we have done here. We're trying to do here. We're trying to construct this adjacency list using the vertices.
From 1 to 37, it is all the edges and all the vertices. It is there, right? From 1 to 37, line number 1 to 37.
Line number 1 to 37.
No, not 1. From here. Yeah.
This you are saying?
Yeah. 21 to 37. Here, this vegeted means every node and every edges are there in this, right?
Yeah, this is the normal BFS function we talked about a little later, right? So we'll use this function later on in this but I've just written this function. This is the exact same function given in the lecture. If there is an adjacency list and if it is given an input v, it will find from that v wherever we can reach. The visited will give, whether a dictionary will give the reachability of this node v.
Right. BFS, yeah. What BFS does is okay.
right? So that will be returned using this function. We'll use this function later on.
Yeah, yeah, okay, okay, okay.
So
And now
this,
come,
yeah, so this is the adjacency list. We have used these vertices and edges input and converted it into an adjacency list. Okay, so that is what this much is. Okay, so now what should we do?
Sir, shouldn't we be writing a list of j dot append I, because it's undirected list. It should be connected both ways.
Very good, very good. That is a good point. So this is also a valid. What he said is a valid point. Since this is an undirected graph, and we are only so we have to add the other direction as well, right? So this is what you said, right? Not append. I.
Yes, sir.
So this will give the second direction. So both directions. Since this is an undirected graph is given in the question. So you have to read the question carefully. This is an undirected graph. So given an undirected graph. So since it is given an undirected graph, we have to write, we have to include both edges in the adjacency list. Okay. So that is a very good point. Otherwise, if you don't include this, we can see later. Not all test case will not pass. Okay, so let's just check our adjacency list one, whether it is working or not. We can in between we can just keep printing, just check whether till here we have done it correctly or not. This is a good way to write your codes. So later on at the end we don't see it like so. We can see there is this connection 1, 3 edge is there, 3 to 4 and 3 to 7. 3 to 4, 3, 1, 4, 7 is there because it is an undirected graph. 4 to 3 is there. Yeah. So this is the adjacency list we got. Okay. This is the adjacency list. So the list is correct. This is clear, right? Till here, I hope it is clear.
Yes.
Now, okay. Now the component part. So let's we need something to mark the component, right? Let's component. We need to count the component. Let's say comp ID counts the components. Okay, this is to count the components. We'll use this just to count the components. Okay. So how do we approach this problem? So we'll start at say any vertex. So let's say we started here. So I'll just write this part of the code and then explain it to you. Okay. That's the two variable. One is component, one is scene. I'll tell you why I've used this. So we'll use a while loop. So length of word. Okay. So here the scene variable counts the number of vertices that we have seen. For example, in the first case, we start our BFS here. We see 1, we see 3, we see 4 and 7. So this will count 1, 2, 3, 4. Okay, this will just count the 4. And if it is less than length of vertices, what is the length of vertices? 8. If it is less than 8, then we have to start the BFS again, right? Can you see this part? For example, so when we first start the BFS at 1, we see this tree 1, 3, 4, 7 will get searched. Then how do we know we have to even go again, like go further? For that, for example, if there is 8 vertices in this list and we have covered 4 of them, So we know that still there are more vertices left. So to keep track of that, we'll use this scene variable. So when scene becomes the length of vertices, then it means we have covered all the vertices. Okay. Is this clear?
Sir,
No, sir.
Yes.
first of all, scene start from 0. Vertex is
Yeah.
starting from 1 to 8, right? Is it starting from 0 to 8?
Yeah. It will. So we'll use we are using this while loop to so this while loop will terminate when scene will reach the length of vertices. So we'll cover all the vertices. When we cover all the vertices.
I think it
Got
would be length of -1.
Length of, so 8 vertices are there, so that's why we are using less than, right? So when we reach 8, it will stop.
Okay.
Yeah, we can we'll see this. Okay, now we need the starting vertex, right? Where to start? We need to start somewhere.
Yes. But how do I pick first element?
Okay, so this is a confusion. Now where do we like start? We can start from anywhere, but once let's say we have started at 1, 3, 4 and 7 are done, then we need to move on to 5, right? How do we find this node?
DFS graph. If I call DFS graph,
Yeah, but how do we find the V that is required to call this V is required, right, to call the BFS?
yes.
So how do we do that? Any idea?
I think how we can pick lowest element.
Lowest element, okay.
But how do I pick?
Okay. So, but we do not have the visited that is there here, right? So how do we know that we need to pick? Yeah, okay. So let me just write this much of the code and then I'll explain to you. Let's create a different dictionary called component. It just keeps track of the component. And I'll just initialize it. This is just the initialization. So this is basically, it is doing the same thing as the visited, but the visited is here. We need to keep track of whichever node is seen, right? Once we see this, we see this, we see this, we need to keep track of that. So that is what this component will do. Once we see a component, then we'll mark it. Okay, so starting what is this?
Pardon, sir. How we shifted from?
Yeah, I'll tell you why it is used. Okay, I'll just write this much of code and I'll tell you.
Okay.
I for if we take okay, so this starting vertex, we are just trying to find the starting vertex. So it will iterate through all the in the A list of keys, like for all the keys, like in the A list, if the component is -1, component, okay, we'll use this. So if its component is, so this is what we are doing here is, if for example, if this much as the BFS is run, 1, 3, 4, 7 is completed, then it will give the list of all the remaining part of the graph that is not that is not been seen yet. That is what we are trying to do from here, from this component. We'll use this component dictionary to keep track of all the unseen part of the graph. Is this clear?
Why -1 is there?
So -1, because we have initialized component as -1. So
Okay,
if it is -1, that means that part is not visited yet. Okay, so I'll explain it at the end. Once the whole code is completed, it will be easier to see. So we'll start with we'll call the BFS BFS function on the list, and the first node in this list. So initially this component dictionary, that start v will contain all the full graph. So we can start anywhere, right? So we'll just take the first, for example, first I from it, that is the first starting v of 0, and then we start the BFS. Is there any confusion here? We are starting the BFS from all the components that has not been seen yet. From the first one, like from any one of it. It doesn't make any difference, right? Because we are trying to find from where all we can reach from that component. So it doesn't matter from which component we start, as soon as it is not seen yet.
Means this A list is now having the vertices, the dictionary. A list is a dictionary which is having the vertices has not been seen. Is it so?
A list is just the adjacency list representation of our input.
Okay.
We are using this A list and the starting vertex that we have just found out from this list. Like so this is so we just think as we A list and we are starting with any vertex, right? It doesn't matter. We are using A list is just this representation of this graph.
Yeah.
And we are starting, say, from anywhere we can start, right? We can just start from 3, we can start from 6, we can start from 2. Just we take the whole set of, and we start a BFS, say we are starting from 3. If we start BFS from 3, the first set of BFS will scan 1, 4, and 7, right?
Right.
And then this part is gone. Then we start the BFS again from, say, 5, and then we get a second component. And then we start the BFS from 2, and there is only 1. So we get 3 components. Is that clear?
Okay, how is the previous question? How we are switching from first component to second component?
Yeah. So that, let me just complete the full code. Then maybe it will be much clearer,
Okay.
since I'm stuck here.
Okay.
So maybe you're not able to understand.
Fine.
Yeah. So now we have called the BFS. So now let's.
Hello, sir.
Yeah?
Can we just do we use visited dictionary and use for loop? If the node is not visited, then we start BFS graph, and again we in another loop we keep on seeing if it is visited. If it is not visited, then again we can do.
Yeah, but we do not have visited here, right? Visited is is in the BFS function. How do we start? You are saying we can randomly start from anywhere.
From the first node of visited, which is false, of course.
Okay, but where is visited? Visited is in this function, right? BFS function. So it is just so it is
We
like
can make it global. We can make it global. The nodes which get visited get true, and the not visited we can use them.
I think we can do that way also. Yeah, that is true. Yeah, you can. You are saying you keep a visited dictionary as a global variable, and then we use it, right?
Yes, yes.
Yeah. So I am just doing the same thing, but I've just used a different name, component. So that is just the implementation. But yeah, you do it that way also. But this is almost the same approach. So I'll just finish this code. So if you do that again, we'll have to make a lot of changes. So I'll just finish this code and I'll explain it to you, since I think it is maybe other sessions will also start soon. So I'll just try to write this code and then I'll explain it to you. You can do it that way as well.
Okay.
It is all implementation. It's just the logic you need to understand. Okay, I'll just finish this. So in the key, we'll just check. Okay. All right. So, okay. So this part of the code is just iterating through we got this visited, right? After running the BFS, we get the visited from this node. And using this visited, we see the keys of this visited, in which if the visited is if that visited dictionary, the key is true. If visited of Y means we are just checking whether it is true or not. If it is true, then we'll increment this scene. This is just for component. You can just even this doesn't really matter. Component of I. Okay, this component of Y, we are giving the component ID. So for example, in the beginning, we are starting 0, right? For example, component is -1 first. So okay, I think I made some mistake here. Component ID is initially 0. Yeah, component ID is initially 0. And then we give the first set will give the component ID of, so for example, if we start at 1, we give the component of so one's component will be 0. So we start from 0. All these are in the 0th component. So 1, 3, 4, 7 are 0th component. So we'll just give the component of 1 as 0. We'll give the component of 3 as 0. Give the component of 4 as 0. Component of 7 as 0. So this means once we give a component, that means the component is no longer -1, right? So when we start again, when we find the start V again, so if it is not -1, that means this list will not include those 4 nodes.
Yes, sir.
Right. So because we need to start the second set of DFS, not including the first 4 nodes. So since we have given the component ID to those this component of Y, so that will automatically remove them. So this is to get the remaining of the nodes. Is why we have used this component dictionary. Okay. Now we need a terminating condition for this find component undirected graph. So that we can give here, because when this start, V, start vertex, when it is an empty list, that means all the components has been scanned. And we can just return the comp ID. Component ID. Component ID is component ID will be incremented when we finish all the first BFS is finished. Then we increment the component ID after giving the component ID to each component. Right. And we can also return here just for the function to end. So I think there are some doubts here. So is there which all part is it like which is not really clear? Is there any part which is not clear in this?
The component part is not clear. Component part is not clear.
Okay, component part. Okay. So all right. So this component, why I've used this? So we need to find. So once we run a set of BFS, then we need to find the remaining next node to start, right? How do we find the next node to start the BFS? Suppose we run a BFS on 1 first, then we get the first set of components. So this is 1, 3, 4, 7 is over. But how do we start at 5? Next set of nodes, 5, 6, 8, or 2. It doesn't matter wherever you start from. But how do we know where, like, how do we start? How do we find this node? Next node to start BFS from? So that part is why we are using this component. So initially all the because so someone said about visited node, but we cannot use visited, right? Because the visited is, so every time we run the BFS, the visited changes. Because visited will, initially, when we run the BFS here, only 1, 3, 4, 7 are the visited, right? Then we again run the BFS, 5, 6, 8 are the visited. So visited will keep on changing. We cannot use visited in this case, right? Since it is not declared globally. So we are starting the BFS with the list and the starting. So this start V is a list. So we are starting just from the first element of this list. We need to start the next set of BFS. So in the beginning, it will be the start we will give every vertex. So then we go to this part of the loop and we change the component of I in the first set of BFS, whichever visited has been set to true. So we check that visited of I. Visited of I means visited of I is true or not. If it is true, we change the scene and the component we change from -1 to component ID. So first set will have 0, and then we increment the component ID. Is this clear? The component is clear now. Why we are using it? We are using this component dictionary to find the next set of nodes after running each BFS. Yeah, I think there are more confusion. I can explain again if you want.
Yes, sir. I think it is clear. And in the end, we just count how many different values the component has.
Yeah, we just return the component ID. Component ID, right? Component ID is just being incremented every time one component is there.
Yes.
Yeah. So did you understand the component part?
Yes, sir.
So can you try to explain it? Maybe what I am trying to do, they're not understanding. Can you just try to explain it? Doesn't matter if it is wrong or correct.
Yes.
Sir. 56 line and 57. what is doing here? Start if. Yeah. If the code is if comes first, na sir. Condition is if.
Okay. You are not understanding this terminology. So this is like we are choosing I. So for this is equivalent to, this is same as writing this.
Okay, please.
So for I in a list dot keys. Okay. So if component of I is equal to -1, we put in the start v. So start v is equal to initially it is so this is equivalent to this. We are first initializing a start v list for every I in a list of key. We are checking if its component is -1. If it is okay, I did some mistake here.
Component is -1.
Yeah. So initially all the components are -1, right? So component will change the component to component ID when it has been seen from the BFS search. Right. So once it is like each component is seen. So once these 4 are seen, then we need to that start we will give 5, 6, 8, and 2 in a list. And then we take the initial first of it and run the BFS again. We start v of 0 will take and run the BFS again. So start v is basically we are a starting vertex. We are trying to find the next starting vertex for the BFS for the BFS next set of BFS. We are trying to find the starting vertex.
But start v you are taking as a list, na sir? Here you have
we are sending only the first one, right? Start v of 0, we are giving it to the BFS.
Yeah, start v of 0.
Yeah.
First one.
First one. You can take any one, it doesn't matter. But because it is an undirected graph, we can start the BFS at 6, at 3, at 4, it doesn't matter. We can start it anywhere. Yeah. There was some error. We'll just correct it. Line 64. Oh, I think the line would have changed now because we have added more code. '68. It's 68.
So it would be keys.
Yeah, right. Right. Public has passed. Yeah, the private has passed. Okay, so I think this is a very confusing, code. Is there any more confusion, like how we are, if there are more confusion, like we can clear it? I think it's not fully clear yet. Is there any more confusion? Like what we have done here? Okay, great. So this is the first PPA. The second PPA is very not that big. It is a small code only, but yeah, we'll use DFS in the second PPA. Okay. So let me just quickly read through the question. So complete the Python function, find all paths. To find all possible paths from the source vertex to the destination vertex, in a directed graph. So it is a directed graph here. So function find all paths with the given inputs takes vertices as a list of vertices. Glist is a dictionary. It is an adjacency list. Okay, representation of graph, edges, source vertex and the destination vertex. Okay, starting vertex and the destination vertex. And it should return the list of all paths from source to destination. The return value will be a list of lists where every path in a sequence of vertices, every path is a sequence of vertices as a list. Return an empty list if no path exists. Okay, so this is vertices. Vertices are the set of vertices. Glist is an adjacency list, and we are given a source and a destination node. Okay, so we have to find all the paths from source to destination. For example, if you are given 1 and 2, source is 1 and destination is 2, we have to find all possible paths from 1 to 2, like 1 to 3, 3 to 6, and 6 to 2. And we have to return them. Is the question clear? What we have to do here?
What is glist, sir? Glist?
Glist? Adjacency list, right? Of the graph. Adjacency list representation of the graph. Okay. Oh, I avoided. Okay, so how do we do this? Like, what can we use here? Like, how can we find this out? And what method can we use to find this? Does anyone have any idea?
Depth first search.
Depth first search, right? So how do we use the depth first search?
I need to adjacency. I need to create adjacency list, another adjacency list. Not
Adjacency list is already given, right?
okay. I need to return list of lists, right?
Yeah, you have to find, okay, the first list, each path should be a list. 1, 3, 6, 2, like first path is 1, 3, 6, 2 is a path. 1, 4, 6, 2 is another path. 1, 4, 6, 2 is the second path. Third path is 1, 4, 7, 5, 6, 2. So this is the last path, the last end. We can. This is the example. So how do we implement the DFS? For example, we have given source and destination as well. The two nodes we are given, that is source node and destination node. So here on the first example, source node is 1, the destination node is 2. So how do we use this data and see, like, how can we implement DFS to find all the path between 2 points, 2 nodes? Any idea? It doesn't matter if it is wrong or something. We can just correct it as we go on. So what will happen if we run a DFS at 1?
It will take 4, 3 and 4, 2 vertex. I will go, and each time I will give visited. But
no, that
how
so
I can confirm?
First,
Yes.
you just run the 1, 3,
1, 3, yeah.
6,
So 6,
and then 2.
2, right? So yeah, so since this is DFS, we are not we are going depth wise. We are not using breadth search. So we'll go from 1, then we go to 3, and we suspend 1, and then we go to 6, we suspend 3, and then we go to 2. Right. So we have found one path. But how do we use this to find multiple paths? Do you have any like, how can we use the same thing to find all the paths from 1 to 2? Like, or if not DFS, anyway, like, how can we use anything to, like, is there any way you can think of to find multiple paths in the graph?
removing the in between vertices.
Okay, okay. So which vertex should I remove? So if I start first, 1, 3, 6, 2 is the first path.
Three
Then
and,
which should I remove?
3 and 6.
3 and 6. Okay. For example, if I remove 3 and 6, then what will happen? Then can we
No,
find the other paths?
no, no, no.
No, right? Because 6, we need 6, right? 1, 4, 6, 2 is the second path. But we can't, if you remove 6, you'll not be able to find that. Okay, so
Hello, sir.
yeah.
I will remove those vectors which has two indicators.
We can use depth first
Only
search. We start from vertex 1, and as we visit the node, we add it in a list, and then we go for the next node, and then again. And if we reach 2, then we print that list or store that list or listed. Otherwise, we restart it for another path.
There
Right.
is
So
a condition.
yeah. What?
There is a condition. We should not visit vertices twice.
No, there is no condition as such. We can use same vertex twice. The only condition is there should be different paths. No. Okay, so the person above before was saying you have to start from here, go to 3, like, and then once we reach the path, once we reach the first path, then what to do?
Otherwise, we
I couldn't hear that.
We can keep a list of the starting vertex, and first we started from 1, 3, 6, 2. Then
Okay.
we will continue to the next vertices in that adjacency list. The 4 will come. Again, the same recursion will take place for 3 and 4 also. Is it so?
Right. That is correct. So we start at 1, we go to 3, we go to 6, we go to 2, right? Then once we reach the destination, the first path is done. Then we go back to 6. Is that what you're saying?
No.
Then?
I'm saying that maintain a list of adjacency list of a dictionary of all the vertices which are having the connected nodes. The one will have 3 and 4. We have started from 1. We started from 1, went to 3, and then 6, then 2. One part is complete. Then we will go again go to 1. The next left part was 4. Then we will start with 4.
Okay.
1 to 4. 1 to 4.
Or sir, we can do like first path is 1, 3, 6, 2. So according to DFS, first we will discard this 2 and then we get back to the 6. We will see the neighbors of 6. If there are, then we make that path a different path. If there is no neighbor of 6, then we discard 6 as well and then we go to the 3. If there are the neighbors of 3, then that will make the other path. If there are no neighbors of 3, then we get back to the 1. If there are neighbors of 1, then that path will make other path. 1, 4, then we will check 4, 6.
Yeah.
And then again 2.
Right. Okay, and then we go back. Okay. So that is the correct implementation. That is a good example. So this is what you have to do. You have to start at 1. So backtrack, right? You have to use a stack. So someone also said about recursion. So we can use recursion as this stack. So we start at 1. We keep on putting, like, put it. That is how DFS work, right? We start 1, then we see the neighbor node 3. So then we put 1 back. We put 1 into the stack, and then we see the neighbors of 3 go to 6. We put 3 in the stack, and then we take 6 and then go to 2. So once 2 is done, that is a once we see the destination, we backtrack. We go to 6, there are no neighbors of 6. Go back, go to 1 again, then find next path. And we keep on doing till we run out of everything. Right? But we should also be careful about this reverse. So we should not go back to we should not be in a loop. We can see that. Like we should not run around in a loop as well. So for that, we'll have to keep track of whatever we have seen yet.
Yeah, this track is required. 1367 is maintained. So how this blueprint should prepared is to write the code. This is the problem. The blueprint, to prepare the blueprint to write the code.
Right. Yeah, that so once you get this logic, then so you already know how DFS work, right?
Yeah.
So we are roughly using the same logic as DFS here. The DFS, how we use DFS, we are using the same implementation almost similarly, but to find the path. So once we get this logic, then we can start working on the code, right? So this is the blueprint, like this process. Now we have to convert it into the code. Okay. Okay, let's try to work it.
So we have another class, so we can leave or attend that one.
Yeah. If you have any other sessions from the instructor, you can leave. Don't miss them.
Okay, thank you.
The recording will be available, yeah, if you want.
Now this PDS live sessions will be 4 to 6 or 8 to 10 will be also continue.
No, this is just the PPA session, no PPA session that I take. But the main sessions are the other one, one on Friday and another one on Wednesday, right?
Yeah. That one will continue, na sir?
Yeah, that one will continue definitely.
And PPA you will continue from 4 to 6. Okay.
Yeah, 4 to 6 on Tuesdays only.
Okay. Yeah. On Tuesday.
Yeah, so this is just like a refresher. So you can use this session as something to add. So when you go to the next session, that will be much clearer there.
No, sir. It is very much required because without having the concept, going to the code is not, I think, valid.
Right.
This is very good session. The concept we are confusing, but that will be, I think, practice. It will help in that.
Yeah, maybe PPA 1, I think that was a little confusing, that component part, right? So once you write the code,
I will do it again.
Yeah, you see this code, once you write it without component, then you will understand why I wrote that component. Because when you write the code, you will understand what you are not able to do, like on a certain piece of code. For example, if you don't use that component, so you will not be able to find the next starting vertex, right? So this you will only understand when you write this code yourself. So as and when I started writing the code, I understood, like I'll figure out that this is required to do this part of this coding. So because I already know how to code it, so I said it. So you are not able to understand that part. So once you code it yourself, you will understand why it is required.
Right.
Okay. So this is not that big of a code. I'll just maybe other sessions are there, I guess. So I'll try to finish it a little faster.
Yeah.
So we'll write the find all path. Find all paths. What is okay?
Sir, one thing we can can you sequence the class? First of all, general discussion, then PPA, then you can say coding part. The fourth, I think after the 4th week or 4th week is running. After the 4th week, can you do that thing? First of all, discuss all the theory, then going to the code. I think that would be much more better.
I discussed the theory, right? I gave a rough idea. Did you
Yes,
join
rough
late?
idea. Yes.
You came? Did you join late? I gave it in
Yes,
the.
I joined a little bit late.
Okay, I gave it like in the first half an hour or so. I gave.
Okay, 1 hour later. Yes.
Yeah. In the beginning, I gave a rough idea because since this is like 8 lectures are there, so I can't fully explain it in a 2-hour session. So I tried to give a rough idea in the beginning.
Okay, sir.
And I also see that most of the people have not watched the lectures yet. So once you watch the lectures, no, it will be much more easier. The reason you are finding it difficult is because you haven't watched the lectures on completely.
Yes.
Okay. Yeah.
Can we have one more session from you?
Yeah.
Weekly one.
One more session.
Yeah.
For the PPS.
2 hours, it's difficult to cover all 1 week.
Right, but there are 2 more sessions, right?
No, from you, I am saying from you.
I'll convey this to the instructors, like maybe not official, maybe we can have an unofficial session wherein which is not recorded. If you have doubts and all, we can clear there. I'll try to get that. If that is fine.
Only 2 sessions for the coding part is, I think, insufficient.
Yeah. So maybe we can have a small doubt clearing sessions or anything, like wherein like not it like
that
we can. Yeah, like Nikhil asked, right, for the session.
Yes, I also need to do that, sir.
Okay. I'll talk to the PODs and then I'll get back on this. Okay, maybe.
Okay, sir.
Yeah. So let's try to. So this is the DFS implementation we are trying to do, right? So okay. So we're trying to find that. Oh, it is already here. Just copy this. This is the function we are trying to write. I'll just write the same exact vertices, glist, source, and destination. Okay. Oh, now we have to write a DFS, right? Which returns. It should return path. Paths, multiple paths, right? All these paths it has to return as a list of list. So let's write that DFS. Let's say we have a DFS. So the DFS should have this glist. This is the adjacency list. And it should have the vertex, right? Starting vertex. Source, destination, and yeah, this should be enough, I guess. Okay, so how do we think we can implement this? Or should I just write the code and then explain?
No, please explain, then write the code.
Okay, so so this is what we have to do, right? We have to first start here. Start at starting node. This is the starting. One is the starting node, and 2 is the destination. So we start at 1. We go to 3, 6, 2. We find the first path. So we append this path 1, 3, 6, 2 into the paths list, for example, say. Then we have to backtrack to 6 and see whether 6 has any more neighbors. Since 6 doesn't have any more neighbors, we'll backtrack to 3. 3 also doesn't have any more neighbors. This is an incoming. So
Yes.
3 doesn't have.
Arguing.
So we go back to 1. But 1 has a neighbor, right? 4 is a neighbor. So now we go from 1 to 4. From 4 to 6. And 6 to 2. So we find the second path. We add this to our path list. And then we backtrack again to 6 and to 4. Now we come to 7. Because 4 has a neighbor 7. We go to 5. And we have to go to 6. We should not go back to 4. So we go to 6 and we go to 2. Then we backtrack and check there are no more nodes. Right. So this is the implementation we have to do. DFS implementation.
Okay, got it, sir.
Yeah. So since recursion, so this backtracking, like we discussed in the starting, is done using stack, right? Stack.
Yes, recursions. Stack.
Yeah. Stack is basically recursion implements
Yes.
stack. Yeah.
Yes.
Okay. All right. So this is what we are trying to implement. Okay. So if so we'll see the terminating case, right? If a vertex or so we'll just give this vertex. This is the vertex. Again, if the vertex is equal to the destination, test, then the path is complete, right? If we start, so this is the terminating condition. So if we start at 1 and we reach 2, once we reach 2, that is the end. That path is complete, right?
Yes.
Right. So how do we keep track of that path also? We need
Put
to
it
keep,
into the list is good or dictionary. I think dictionary would be good.
okay, to keep track of path.
Keep track of list. List of dictionary. Best.
List, right? List. We'll keep all this, like as and when we are going forward, like we are starting from 1, we go to 3. So we
Yes,
add,
that will be under the inside the list.
inside a list, we'll keep track of 1 to 3. And then when we go to 6, we put 6 into that path. And when we reach 2, that is the destination. 2 is the destination. So if we reach 2, we know that this path is complete. So we include 2 to 6, and then we add that path to our path list. To our final, we have to give a list of lists, right? So for example,
Yes.
let's say we use this paths as the final list of list, and we use a variable path that stores the individual list. Okay, so this path will store the individual list. Okay, so let's say for v in G list of vertex, and okay, so I'll just write this part of the code and I'll explain it to you. So this is very simple. Once I'll explain it, it will be easier to understand. We'll call the same function again. We'll try to implement it as a stack. And vertex. Okay, vertex. We change the vertex, and the destination will be same. Okay, so now we also need to pass the new path, right? So that I'll just write this and then explain. Otherwise, it will be very confusing. So So this is the DFS implementation, and we'll call this DFS here. Okay. Vertex will be the source. We first call with the source and the destination and the path. So first path will be the source node itself. So this is like an initialization. I'll explain it to you what I've done here. And the okay. This is the terminating condition.
So it would be path dot append, not paths.
Yeah. So I'll tell you, the paths is the list of list. Okay, so we will keep a global variable that is the list of lists. Okay.
Okay.
So in this list of list, you have to add the individual paths, right? For that, we'll run this DFS recursion function. So what it will do is, this has the adjacency list, the vertex, the destination, and the path. So initially, in the beginning, we'll pass the glist, the source. The source will be, for example, in the above case, it was 1, right? In the above example, it was 1. So starting vertex is the first thing we'll pass into this function. Source, destination, and only the list containing the source. That will be the path. So initially, so in the first step, when we start, the first we are starting at 1. So the path is just 1, right? Then we go to the next neighbor, we see 3, and we add 3 to the path. So to do that, so initially we'll pass the source, that is the starting, as the path to this function. So so this is the terminating condition. We'll come back to this later. So for v in, so it will check the vertex. So the this line number 9 is to check the neighbors, right? The glist of vertex is checking all the neighbors, and v is giving the neighbor, first neighbor. Like v in glist, this is the finding the neighbor. If v is not in path, then we call the GFS again, but this time we are adding the new v to the path, and we are changing the next vertex. So for example, initially we are starting at 1, and then we see the neighbors of 1. The first neighbor of 1 is 3, right? So we see 3. First neighbor of 1 is 3. So first 3 will be v. So 3 is not in the path yet, because the path only has 1 now. We have passed only the source. So since p is not in the path, we call this function again. That is, we call the DFS again, this time with the 3 as the vertex and the path as the 1 plus 3. So we call this again. So this function will again come here, and we will check the next. So what we are trying to do, that stack implementation is what we are trying to do using this method. Are you understanding this part? So we are trying to implement the stack, and it will, when the vertex is equal to destination, this is when this DFS function will stop. That is when it will find the destination 2. It will reach to 2. Then it will just return. That function will just return, and since the path, so when when the vertex is equal to destination, we'll add this the path that we kept on adding, like after every vertex we kept on adding a path, right? So that we'll add to the global path. That is the list of list. So this path is a list. We'll append it to this path, paths, THS. Okay, so THS is the main, which has the list of list. So we keep on adding it to it. And at the end of it, we'll return the paths. When whole of the graph is completely, like we check each and every path. So
I understood. So, but here, if it is undirected graph, we can use.
no, in the question it is given, right?
Yes, and I'm thinking if it is undirected graph, we can't use this stack method, right?
If it is an undirected graph, why will not be able to use? We can use, right?
If it is undirected graph, let's say there is a 3 6, right? 3 6 6 3 will be there, right?
3 6 6 3.
Yes. Let's say in a stack, if I reach
No. So that is why we are including this one condition here, right? If V is not in the path. So if it is already in the path, then it will not. So if it is an undirected,
it will be lose stack after this list into the global variable, then it will be lose this information, right?
which information?
That path information, whatever path here, this list will be append. That path information will be gone.
Yeah. That is no. It won't be gone, right? So it will backtrack. So every time it backtracks, it will be one less. So for example, when it backtracks, that is why we are using this recursion. So initially the path is 1. When it is at 3, it is 1 3. When it is at 6, it is 1 3 6, and 2 it is 1 3 6 2. But when it is backtracking,
it would be work. Yes.
Yeah. So this 2 will not be there. So it will only this much. It will come back here. It will come back. It will only be 1, and then it will go to 1 4 1 6 1 2. So are you able to understand this implementation? Like, is there any more doubts? Why it works? Okay, I haven't run it yet.
If we use undirected graph, then it will be exceed the limit of recursions.
Undirected graph.
Because every if it is a reach to the 2, then it will be go to the 6, then check 6 never, then 6 never, here is a 3, let's say 2 6 6 2 also there, right?
Right. It will go back to 4. You're saying? Oh yeah.
It will be do lots of recursions, right?
Yeah. So undirected graph, it will not work.
Yes, it will be exceed the limit.
No, it will work, right? So if it is 1 3 6 2, and it will backtrack to 6. You're saying?
If it is a vector to 6, but 6 is a here in directed graph 6 1 yes 2 6 6 2 6 2 will be not counted.
You can try. No, you can try.
Yes, I'll try. Okay,
I use this code and create a graph that is undirected and try.
Yes, I'll let you know.
I think it should work. Yeah. So okay, we have some other invalid syntax. Line 17. What's wrong with line 17? Oh.
Okay, function name is not there, nice.
Yeah.
You didn't store this information. Okay, GList is not defined. Okay, let's check.
17.
GList is not defined. Say that. Okay, capital G, it would be right.
Oh yes. They make the same mistake again somewhere else.
No, after that it will change, right?
Oh yeah, right. It is calling.
Yeah, that's fine. It will be fine.
This should work. Okay. So is this clear? Like, are there any more doubts regarding this?
Yes, sir. That's great. Good.
Right. So this is a quick. So this is how you can use recursion. Whenever there is a stack implementation, you can always try to use recursion.
Yeah, we will try this code because without writing it at our own, we will not be able to understand the coding, live coding OPP sessions.
Yes, yes, sure. So PPA 3 is a little, like, it is a different PPA. Okay, so it is a maze solver. It is a challenger question. So I will. This is not really using. This is using whatever we have studied till now, but this is a little advanced. So
We
I
will
would
do
like.
in the last. We
Sorry.
will do in the last sessions. We will do in the last session. So, once we are conversant with all these things, na, then
Yes,
we will
yes.
do.
So yeah, this will be a very fun one to do. So it will require a little bit of creativity. So we'll recommend you all to go through this and do it later.
Okay.
You can like, if there is any doubt, please ask the Discourse forum. Is that fine? Because if I solve this, you will lose the fun of it.
Okay, we will do, but after doing other PPS, then we will do the PPA 3.
Yeah, yeah. So start with the 1, 2, and then come to it.
Okay.
Okay, sir. Can I ask one doubt? I have a doubt in you can say linked list.
Sure, sure. Go ahead.
My can I share my screen? So it will be.
Okay, okay. Wait
Can I
a
do that?
second. Yeah, yeah. 1 second. I'll just stop mine. Yeah, sure. So like, rest. If you all have any more doubts, you can ask here. Otherwise, if you want to leave, you can also leave. It's fine. Yeah. So who I want to share, please share. Go ahead.
Yes, I'm sharing. I'm opening. In this, I think this is the week. Sorry, sir. Can you see in this
Yes,
code? If I take last dot next equals to new node, then it will be giving error. Why? Last is a reference, right? So last dot next, I have a I can give that reference into the new node, and I can do new node is equals to the last node.
Okay, okay. So can you just try to tell me what you have done starting?
Here I'm inserting, right? Inserting the end.
Or
So I'm
1 second. Just run the code once. I'll just see what the error is.
okay. I run here. This none type. Next dot none type. So whatever given cell dot last dot next, then it will be giving error. If I change the sequence, it is giving the error. So why?
None type. Okay. Okay, okay. Go back again. Last dot next.
Yes. Last I have
Okay. How can you have last dot next? Last is the last element, right?
last is the last element, but after the last I have a none belief, right? I have a reference. In every node, I have a three thing, right? Data, next, and previous. So last dot
Yes.
next, I have a reference, right? I can give it that reference into the new node.
Okay, okay. Oh, you're saying last node dot next is
Yes,
equal to
last
new
node
node.
dot. I tried multiple code, but when I give in last dot next, it is giving error.
Okay.
But logic wise, I think, am I losing logic? Logic wise, it will be work, I think. Why it is not?
First, you're initializing. Okay, so first case is when there is no node, right?
Yes. Yes, no node. That I am giving
Second, second
is
is second
one
case is
element,
one element. Okay.
and third is else is other than that.
Mhm. And the thing is, so can you write self last dot next is equal to new node is not like so since there is only one node.
Hmm.
Wait a second, let me just check once.
This logic, no, my question is, this logic is not working. Why?
Yeah, I'll just figure it out once again. This is week 3, right?
Yes, week 3. First question.
The double linked list.
Yes, if I do the new node dot previous equals to next last server last, then it will be work. But reverse it is not work.
Yeah. So you are trying to do the last dot next as new
Next.
nodes first.
But this logic is not working. I don't know what is the logic behind it.
Okay, self dot last is equal to new node. I'll have to look at this once.
Okay.
Can you post this in Discourse? I'll just check once and then get back to you.
Okay, I will share this code.
Yeah, I just copy paste it
Okay, I'll
in
do that.
Discourse and just ask them.
Yes.
I do feel like why is it not working? I think there should
Yes,
be
I
something.
searched in YouTube also, but I didn't get anything.
Okay. I'll just check once. I'm not able to figure it out right now.
Yes, that is anyway. I cannot. I searched it, but I didn't find out what is the logic behind that.
Right. Okay. So anyway, so I think is there any more doubts if you are
No,
having
no.
any?
In linked list, I have a doubt. Okay, I have another doubt, so I can ask.
Yeah, maybe I'll stop the recording since we have done with it.
Yes.